So when you do extraction, there's actually a lot of physical chemistry flavors behind the things. When you do your extractions, typically you're going to have a like separation funnel like this. And then you're going to dump in two different solvents. One is phase one, the other one is actually phase two. And then you're going to shake it, and eventually you can enrich the substance that you would like to have in one of the phase. When you do this, typically you will define an equilibrium constant called Kd. This is called the distribution constant. So Kd can be defined as the mole fraction of component I in the phase 1 over the mole fraction of component I in the phase 2. Once you reach equilibrium, the chemical potential of component I in the phase 1 has to equal to chemical potential of component I in the phase 2. You can actually further expand this one using the equation we just derived here. So mu I is going to equal to mu G naught plus RT natural log KH times your XI. So on the first part will be mu G naught plus RT natural log KH I in your phase 1 times your XI in your phase 1. You can write the same thing for the right hand side. Okay, so this part is going to equal to your mu G naught plus RT natural log KHI in your phase 2 times your XI in the phase 2. So once you write these things out, you will realize mu G naught cancels out. RT cancels out. Natural log can be removed. So in the end, what you have is actually your KHI in your phase 1 times your XI in your phase 1. It's going to equal to your KHI in your phase 2 times your XI in your phase 2. Therefore, we know the mole fraction of component I in the phase 1 over the mole fraction of component I in the phase 2 is going to equal to KHI in your phase 1 then KHI in your phase 2. From here, you should be able to see that the mole fractions of component I in a certain phase is actually inverse proportional to its Henry's laws constant. What it means is actually if you have a larger KHI, you're going to have lower solubility. If today you want to do extraction to maximize the content of a specific substance to a specific solvent, then the things you need to do is check out the Henry's laws constant for different solvents. Having this underlying knowledge will help you to actually understand the things you're actually doing. Another application of Henry's law is actually about the gas solubility. So we know gas do not really like to dissolve in the solvent too much. So when you talk about the gas solubility inside the solvent, immediately actually bring you to this non-ideal solution at very dilute condition, which is actually ready to apply the Henry's law to explain the phenomena. Since you know it's going to follow Henry's law, so you know your vapor pressure can be written as your KH times your mole fraction. But for most of the time, when you describe a gas solubility, you do not actually use mole fraction. Most of the time, people actually use molality. So the C is molality, which is going to equal to number of mole of your gas molecule divided by the kilogram of your solvent. So because of that, the K will be different, right? So under this case, you're going to see this thing called the KMH. So this M means actually you're going to have a unit of molality. Okay, so let's talk about some examples. So assuming today you have a container and then you have a water solution, let's say you have H2O. Inside you have 1 atm of CO2. If I give you the Henry's laws constant of CO2 in water is 30 atm, okay, per m naught. Then I want to know what is the CO2 concentration inside the water. This thing is actually very easy to solve, right? Because we know the vapor pressure I of your CO2 is going to equal to your KMH times the concentration of your CO2, right? The concentration of your CO2 is actually just your Pi over your KHM. What is the vapor pressure of CO2 inside this system? 1 atm, right? And then your K match is 30 ATM per M naught. On the top is actually ATM, right? So if you cancel out your unit, you know the answer will be this.